Okay, so thank you. I'm Andy Rudoff from Intel, but actually in this forum where Jim and I were talking about this yesterday, I think this is our 7th forum, I usually come up and talk about what's going on in the NVM programming twig. And yeah, I'm an Intel employee. I work for Intel. I'm holding an Intel DIMM in my hand. But actually a really important aspect of the SNIA programming twig is to be vendor neutral and platform neutral. And actually sometimes it's a little comical. Yesterday in the twig meeting we were coming up with ways of not using the term SFence because that really is an Intel instruction, and you know, we were trying to get a concept across that had to do with store barriers, and we didn't want to make it sound like it was just applying to Intel, and it's a pretty important part of the model. If I you know, make a programming model that only works on an Intel product, which you know, some of you only have samples of and some of you are waiting for and so on, it kind of is less useful than you might think. So the model is written to be used on any kind of a computer, any kind of a platform, whether it's x86 or ARM or Power or Spark or whatever. And it's meant to be used with any kind of persistent memory, whether it's this Optane media or the NVMs that have, you know, some of them have been shipping for years now, right? So that's a very important part of the model. So I just, you know, I'm an Intel employee, but I want to make it very clear that the model is not Intel specific. And so this year we thought we'd do a little bit different than just telling you what the twig is doing. And you know, now that we've had the model out there and supported in both Windows and Linux, you're going to hear about that in the next talk, some of the details. What are some of the experiences that we've had with applications actually being modified? And so I thought I would just go through that. So what I'm going to cover is I'll do a quick slide about what everybody already knows, and you've probably heard now in at least 2 talks. But then there are some parts of the programming model that everybody forgets, and I thought I would remind you what those are, and then talk about are there ways of using persistent memory without modifying your application? Of course there are, and I'll cover some learnings. So what everybody knows? Well, so we've already had at least 2 people up here defining what persistent memory is. And I like to keep it very simple, right? It allows load store access like memory, and it's persistent like storage. We came up with this model when we realized that persistent memory was coming, it was growing. This was, you know, we started the twig many years ago now. And so we've been talking about it for a long time. And in the early twig meetings, we tried to decide, well, how would we define persistent memory? So, you know, when does the model apply to you and when does it not? And so, you know, something that speaks blocks is not persistent memory, but it's actually still covered in our programming model. And a lot of people don't know this, but the programming model was meant to cover all sorts of non-volatile memory. So it was meant to cover SSDs and persistent memory. And there are sections on both. It just so happens that the way you use an SSD is pretty well understood, so we wrote it down, and then we never go back to those sections. We talked just about the persistent memory part. But in our document, we were trying to say, well, should we say that persistent memory is memory that has a certain speed, a certain latency? We don't really want to eliminate some technology just because we don't happen to think that it's fast enough for persistent memory. So we came up with this really kind of weasel-wordy way of looking at it. If somebody would reasonably do loads and stores to it, then the model should apply to them, right? That we're trying to make it something that if you want to do loads and stores, then here we're making a nice vendor-neutral model for you to use. And so, you know, I usually say, well, if it's reasonable that you would just completely stall the CPU waiting for a load to complete, then the model is for you. And you might think, well, it's only reasonable to do that if it's, you know, 350 nanoseconds. Or you might think, actually, I'd be willing to wait many microseconds for that. That's fine. That doesn't matter to me. What matters to me is that if you decide to use load store access, here's the model that we're providing to you. So that's the part that everybody knows. The part that I think is often forgotten is that the whole idea of the programming model is it builds on the storage APIs, right? So every year we show this diagram, or a diagram that looks very much like this. It's the programming model. And the part in the middle there is where you see applications. Yeah, actually, it says the word standard on there 3 times. There's standard raw device access, standard file APIs, and then the standard file APIs on the right-hand side. So why do I have the word standard on there 3 times? It's because the standard file APIs, the way that you access normal storage, applies to persistent memory as well. And so that means, one way that you can use persistent memory is just like pretend it's an SSD, right? That's this middle path here. And we don't give it enough airtime because everybody wants to talk about the load store stuff and the harder programming and how to really, squeeze the most out of persistent memory and leverage what it can do. But, I'm here to tell you, if your application benefits from using these storage APIs and it already uses the storage APIs and it's good enough of a benefit, then you don't have to modify your application. And so my classic example of this is that, I don't know, about 10 years ago, some major applications decided that they wanted to get all the benefit they could out of NAND SSDs. Well, at the time, NAND SSDs were not as big in capacity as they are now, and they were pretty expensive. So they didn't replace storage, right? And so these big applications, they have big data sets that are on their, what I'd call their capacity tier, probably hard drives. And then they had data structures that they kept in memory. And these applications were modified to also introduce the NAND SSD tier, right? So this is for the warmer data that you would fetch it from the hard drives, you'd put it in the NAND SSD so you'd get the benefit of performance. So some of these major applications have been shipping with these features now for years. They have basically a tier where you can put an SSD in. So now imagine this world where we have persistent memory. So you still use memory the same way you do. Maybe you still use hard drives for capacity, your capacity tier, or maybe you use those, those rulers that Frank was showing you that give you a petabyte and a 1U. It doesn't matter. But now your warm data tier can just be persistent memory, right? And the application is literally unmodified. You just are changing the config file that you use to run it, right? You're changing the config file to use where it thinks that you're giving it a NAND SSD, you're really just giving it a persistent memory SSD, fake SSD. So you don't have to modify your app. That's what I'm here to say. Now, what about this other place where I use the word standard? It is also the same storage interfaces, right? Open, close, read, write, all the normal things, except for on the right, this is where you get that DAX-enabled file system path, and it's the same. It just doesn't use any page caching. So if you have an application where you say, well, this direct access storage is so fast, I don't want it cached in DRAM. I want to use my DRAM for something else. All right? I don't want to impose a DRAM footprint. Then you can use this right-hand path, and you're still just using the standard APIs, and maybe the application is still unmodified. Maybe you're just changing a config file to use it. The point is, we didn't have to use any new interfaces. These are interfaces that have been around for many decades, right? Just the standard interfaces. Frank also put a slide up talking about what happens if you just want to use persistent memory for its capacity. So this is where the difference in persistent memory products really comes to play. If you have an NVDIMM-N in your system where it's really DRAM, it performs like DRAM, but it has some extra components to save its state on power loss, then it's probably more expensive than DRAM because you're paying for the DRAM chips and you're paying for the extra logic. If you have one of the new memory technologies, like the thing that we're always waving around from Intel, now you have this large capacity, 3 terabytes per socket, right? It's hard to, if you can even find DIMMs big enough to put 3 terabytes per socket, which you can't yet in DRAM DIMMs, it would be very expensive. So if you're using persistent memory for capacity because it's cheaper than DRAM, then memory mode is one of the ways to use it. You just put the DIMM into memory mode. You can see I drew sort of a cartoon here of how the memory controller decides to either fetch things from the DRAM cache or on a cache miss, it goes out to persistent memory. So no modification to the OS, no modification to the app, everybody just sees a system with huge memory. So there's another way of using it, but it is volatile now, right? Because those DRAM caches lose their contents on power loss. So it is persistent memory, but it's just a volatile use case, right? You don't care that it's persistent in this case. So it's another way of not modifying your app. So kind of to summarize, you know, just again, I think we give a lot of airtime to how to modify your application, and it scares people, and they think, oh my gosh, the only way to use persistent memory is to totally re-architect my application. But we definitely have these ways where you can use persistent memory as a fast SSD, just using the existing storage APIs. If you can still memory map them, right? That's also been in the storage APIs for decades. But if you memory map them, what's happening under the covers is that you're paging the contents into DRAM, which might be what you want, right? If the persistent memory is slower than DRAM, then paging it into DRAM might be what you want for performance. You can use it the same way as I mentioned before, but with DACs, again, they're all just storage APIs, open, close, read, write, mmap. They work as expected, it's just you skip the page cache. Or you can just use it as a large volatile capacity if the product supports it. So then going back to my little diagram here, another thing that I think people maybe don't understand that's worth mentioning is that the programming model, it's not just built on the storage APIs, it's almost 100% the storage APIs. Everything that I've mentioned so far are APIs that have been around forever, right? They're standard APIs. So even if you want to use persistent memory for direct load store access, and you're operating on the right-hand side of that diagram, you open it up, you call mmap or map view a file on Windows, you start doing loads and stores, and you have yet to use an API that isn't standard, right? It's all still standard. When you want to flush the changes out to make sure that something's persistent, you call msync on Linux. Again, standard API. So you have yet to venture into anything that hasn't been a standard for a long time. It's only when you decide, you know, I really think I could flush smaller changes because I'm going to have some persistent memory resident data structure that you venture into this new thing we call optimized flush. Right, so optimized flush is the one thing where you now cross over from being in the standard APIs to something new that hasn't existed forever. And that's because, you know, optimized flush is a way of doing these flushes from user space using instructions that are very fast and very fine-grained. Okay, so that's the crossover, and that's where we start to say, now the programming is more of a challenge. We definitely have applications out there that use the right-hand side of this diagram. They use persistent memory, and some of these are major applications that have announced their support for persistent memory. But they don't use optimized flush. They didn't happen to need it. msync was fast enough for them. It was good enough for what they were trying to do. And so great, right? They had no need for any extra logic other than what you could get from normal APIs. For people who do want to use optimized flush, it is complicated, and it's further complicated by the fact that we make it the application's responsibility to decide if a flush is even required. What if you're on a platform where the CPU caches are considered persistent, right? Then the flush isn't required, and we communicate that using on Intel, we communicate that using an ACPI property. In the model, it says that there's a way for you to check for this, and that's one of the reasons why we did these libraries, is to sort of insulate programs from having to go discover all those ways of checking for things and which instructions are available and so on. So one such library is in PMDK, the Persistent Memory Development Kit. There's a low-level library. You can see it down kind of on the bottom there, LibPM. And its whole purpose in life is to insulate you from having to know these details by checking, well, which instructions are here? Or do I even need to flush caches? Are they flushed automatically? You know, every application has the responsibility to do that, but you certainly don't have to develop that code over and over again. Just use a library, or, you know, we don't care. Take the code out of our library and steal it and put it in your application. We don't care. We're just trying to make persistent memory programming easier. Then on top of that, now this was one of the answers to the questions that Paul got. So what happens if you have state that is bad, right? What happens if you have state that's broken? That's the other, one of the other goals of these libraries are to be able to roll back state into a consistent state. And even more than that, I'm going to re-ask the guy's question in maybe in an even more interesting way. What happens if you get an uncorrectable error? So today, what happens with just normal DRAM? If I'm running my program and I get an uncorrectable error in DRAM, so an ECC error that ECC can't correct, too many bits got corrupted. Well, what typically happens is that the operating system tries to determine if it can continue running or not. You know, is the state so bad that I have to crash the system? But if it can continue running, and it can identify the application that got the uncorrectable, it kills it, right? It sends it an event, a signal. Like on Linux, this is a SIG bus, and the application typically dies. But with persistent memory, what's going to happen? Well, someone's going to say, well, gosh, the app died. They start it back up again. It's going to immediately go back to that same spot and hit that same uncorrectable ECC. So the libraries know about this, right? The libraries know how to detect that the file contains uncorrectables. And they provide APIs for you to discover that and correct it, or at least detect it so that you know you have to go get data from a redundant copy. So we do have an answer, right? We have an answer, but it's in these APIs. Then we've used these APIs to build some higher level libraries. And the one that I'm kind of excited about now is this one called LibPM MKV. It's a key value store. We've built it on top of these other libraries. And it's general purpose. It's not quite product quality yet. That's why I marked it experimental. But it turns out that a lot of people who want to use persistent memory, they don't want to do all the really nitty-gritty detailed stuff that I was talking about in those other libraries. They just want a nice high-level API. I want a persistent memory-aware key value store. With this key value store, we've been able to take the same benchmarks that run on things like RocksDB and get the same performance that we get with RocksDB, only we're immediately consistent, whereas RocksDB gets its performance by being eventually consistent and just doing things in DRAM. So we're pretty excited about this. There's the name of it. Please go play with it. And you know, on top of other things like this, this is another kind of example of Cassandra here. Now, I ask you, did we modify the app or not? I mean, yeah, we modified Cassandra to know about persistent memory. You're going to hear about it in a lot more detail during the Java talk that Steve Dorman's going to do coming up here. It's very interesting. But the app is unmodified. It's just using the Cassandra APIs. Unless you think Cassandra's the app, and then the app is modified. So this is kind of a slide that says, yeah, maybe we're modifying the app, and maybe we're not. Because it's some middleware, right? It's somewhere in the stack. They know about persistent memory, but above that, they don't know that there's persistent memory. They just see a system that's performing better. So you don't always have to modify your app. So you know, what we've really learned is when you go to look at an application for using persistent memory, first look at all the ways of just using it without modifying the app. Maybe some of those are good enough, and oftentimes they are. Then try and use some of the existing APIs, and the higher level, the better. Like try and use the key value API, right? Yeah, or try and use just the storage APIs. Try and use the highest level abstraction possible. And only when you have to, you get sort of pushed down into the nitty and gritty. Okay, I really do want to implement my own hash table that sits in persistent memory. That's fine. You're welcome to do that, and we give you libraries to help you do that. So if you're pushed down into those lower level abstractions, great. And then finally, if you cannot find a library to help you, it's just you really want to manipulate the bits in your own way, then just map it and you have raw access. So you know, start at the highest level abstraction and only go down as necessary. That's what we've learned. Okay, so where are we heading? We're heading into the more of these transparent use cases. We've got some kernel patches coming up in Linux to do some what we think are kind of exciting things down in the memory management layer, again, to make another transparent way of using persistent memory. We're adding more libraries, again, to give you more transparent ways of using it. We're looking at higher level abstractions like the key value store. What other ways are there to do that, especially ways that are idiomatic in other languages like JavaScript and Java and Python and name your favorite language, we're looking at it. And then finally, you know, even the guys who do want to get down into the nuts and bolts of it, we're adding more features. The latest version of that PMDK that I mentioned had dramatic performance improvements in the last release because we went through and tried to find out a way of removing every single cache flush that was in there that could be removed, and you know, we spent a lot of time on that. And what you already heard about from Paul, and I think you're going to hear some more about it later too, is things like remote access, RDMA. What are we doing to make that even faster? It works today. You can use it today, but we can make it faster. We can make it better. So on that, I think I'm down to a couple of minutes for questions. Yeah, thanks.
Thank you, Andy. Questions from the audience? Yes.
Over
you
here.
And then you. Okay.
Yeah.
Go ahead.
So, Nathan Brookwood, Inside 64. You hit a nerve when you held up the DIM and you said, Intel really wants to make sure that we're not doing anything that wouldn't work on a variety of platforms.
Oh, actually, I didn't say that. I'm sorry. Let me correct you. I said the SNIA NVM twig doesn't want to do anything that's Intel specific.
Okay.
Intel, you know.
It's an Intel DIM, you're an Intel employee.
Right.
But
I'm here with my SNIA hat on.
Okay. And my question is, why is Intel regarding the actual electrical protocols for those NVDIMMs as a proprietary architecture as opposed to making it an open architecture so all the platforms can use that?
So Jim Pappas is going to grab the mic from you there.
Well played, Andy.
Also an Intel
Well
employee. You know, I'm an engineer, so there's that was a business decision, and that's why all I can really do is point you to a business person. However, this maybe will help a little bit. In a little act of irony, I'm moderating the session on interconnects later on these 3 interconnects that have all the logos of all these companies that are associated with it, and Intel is kind of missing from those. So you know, we definitely want to encourage that kind of interconnect work.
Okay. Well, if you hadn't said what you said,
Yeah.
I probably wouldn't have asked what I asked.
Yeah, fair enough.
Thank you,
All right.
Nathan.
Another question in the back.
Any other question I can dance around?
So to some of us, the really interesting prospect of non-volatile memory is changing the way applications interact with durability.
Yeah.
Now, if I heard you correctly, most of the emphasis of your talk was on basically giving wise guidance to developers to try to avoid that, right? Only do it when necessary. Only do it when it's appropriate.
Yeah.
To me, the interesting prospect is not making things like Cassandra faster, it's making them unnecessary, right? Reducing the complexity of software stacks by allowing applications to interact with durability through loads and stores. Is Intel planning a richer and more compelling set of showcases for the new style of programming that actually changes the way developers write programs?
Yes, and I think the real issue there is there are many possible avenues, right? And there's a lot of research in academia, and we read it all. And so it's really a matter of time for us to go through and do things like that. So your comment about Cassandra is interesting. You know, because we do tend to take existing applications like Redis or MongoDB or Cassandra and things like that and start by modifying them to use persistent memory so that people can use the same APIs. But actually, the whole reason why we wrote that LibPM MKV was to kind of go the direction you're saying. It's like, wow, that is interesting. We did make a better version of Cassandra, but what if we just threw it all away and said, what would a key value store look like if it was designed from the ground up to be for persistent memory? And I think there's a whole bunch of those, right, of that type of library to write. So I think we're actually just scratching the surface right now. I think we have a...
Yep.
Yeah. Yeah, yeah.
Right.
Yeah,
All right.
I suppose.
We're going to cut off the questions.
Yeah.
It's 10:05, so give the speaker another hand, please.
Thank you.